Every single time you go online, whether you're sending an email, buying something, or just scrolling, there's this invisible shield protecting you. It's called cryptography. And today, we're going to pull back that curtain and show you the fundamental tools that actually make our digital lives possible and secure.
It really all comes down to this one simple but huge question. Think about it. The internet is basically a massive, wide-open public square. Now, if you want to whisper a secret to your friend all the way on the other side, how do you do it without everyone in between hearing every single word? That's the puzzle we're here to solve.
So here's our game plan. We'll start with the absolute basics, how to keep secret secret. Then, we're going to get into the tricky business of sharing keys. After that, we'll talk about creating what's essentially a digital fingerprint for your data. Then we'll figure out how to verify a message is legit. And finally, you'll see how all these pieces snap together to become the very foundation of trust online.
Okay, first things first. Before we can worry about anything else, we have to tackle the eavesdropping problem head-on. We need a way to take a message that anyone can read and just turn it into complete, total gibberish for anybody who isn't supposed to see it.
And the solution, of course, is cryptography. Now, this isn't some newfangled idea. It's an ancient art of making and breaking codes. But today, its main job is to create a kind of digital lockbox around our information, making sure that only the person with the right key can ever open it. So, we've got our digital lockbox. Awesome. But wait a minute. We've just created a brand new problem for ourselves. If I lock a message in that box, I still need to get you the key to unlock it. And if we're using that same public internet, how in the world do I send you the key without some sneaky eavesdropper just grabbing it in transit?
Well, the most straightforward idea is something called symmetric key cryptography. Just think of it like a simple house key. You and I, we have identical copies of the same key. I use my copy to lock the door, and you use your identical copy to unlock it. It's really simple, it makes sense, and best of all, it's super fast.
But here's where that simple idea starts to fall apart. See, one key for two people, easy. But what happens when you have a group of, say, 10 people who all need to talk to each other securely one-on-one? Well, you'd need a totally unique secret key for every single pair of people in that group. That adds up to 45 different keys. It becomes an absolute logistical nightmare, and this whole mess is known as the key distribution problem.
And this is where things get really, really clever. Asymmetric key cryptography solves this problem in such an elegant way. I want you to imagine that everyone gets their own personal mailbox. Now, this mailbox has a slot on the front. That's your public key. It's open to the whole world. Anyone can walk by and drop a message in. But only you have the special, one-of-a-kind key to actually open the box and read what's inside. That's your private key. It's a two-key system, and it is a total game changer.
So let's just put them side by side for a second. Symmetric keys are wicked fast, but managing them is a huge pain. Asymmetric keys, on the other hand, are a lot slower, but they completely solve that key distribution problem. So in the real world, you know what systems do? They actually use both. They use the clever, slow asymmetric key to safely share a fast symmetric key. Then they use that fast key for the rest of the conversation. It's truly the best of both worlds.
All right, we figured out secrecy. We're done, right? Well, not so fast. There's another problem. What if an attacker doesn't just read our message, but they actually intercept it and change it? How do we know that the message we just received is the exact one that was sent? We need a way to guarantee the data's integrity.
The tool for this job is called a hash function. It's pretty amazing. You can feed it any amount of data you want, a single word, the entire works of Shakespeare, a 4K movie, and it will crunch it all down and spit out a short, unique string of letters and numbers. This output, the hash, is like a digital fingerprint. And here's the magic. If even one single bit of that original data changes, the fingerprint changes completely.
Now, for a hash function to be secure, it has to have three very important properties. First, it has to be one way. It's like baking a cake. Once it's done, you can't unbake it to get your original eggs and flour back. Second, if you have a fingerprint, you can't go searching for another file that creates the exact same fingerprint. And third, it has to be practically impossible to find any two different files that just happen to create the same hash. These might sound similar, but these distinctions are absolutely crucial for security.
You've probably heard of some of these, like SHA-256. It's used all over the place. But there's a constant evolution here. Older standards like SHA-1 were great for their time, but eventually weaknesses were found, so we moved on to stronger ones like SHA-256. It really shows this constant cat and mouse game to stay one step ahead of anyone trying to break the system.
Okay, we are so close. We have secrecy thanks to our keys, and we have integrity thanks to our hashes. But now we have to combine them to solve the final piece of the puzzle. How can I be absolutely sure that a message is from you, and at the same time that it hasn't been altered one bit? This is that dual challenge of authenticity and integrity.
And the solution is a message authentication code, or just a MAC. The best way to think of it is as a digital seal of approval that gets attached to your message. It's like the digital equivalent of a wax seal on an old letter. It proves who sent it, and it proves that the seal hasn't been broken.
So how does this recipe work? It's actually pretty simple. You take the message's digital fingerprint, its hash, and you combine it with that shared secret key that only you and the recipient have. The result is a unique, verifiable tag. When the message arrives, the recipient does the exact same calculation on their end. If their tag matches the one you sent, well, that's mathematical proof. The message is authentic and it is untouched. Period.
So let's just zoom out for a second and look at the whole big picture. These things we've been talking about, keys, hashes, MACs, they aren't just separate little tools. They are the fundamental building blocks that, when you layer them all together, create the entire structure of trust that our modern digital world completely relies on.
So let's recap those puzzle pieces one last time. Keys give us secrecy. They're our digital lockbox. Hashes give us integrity. They're the fingerprint proving nothing has changed. And MACs, they bring it all together to give us both integrity and authenticity, proving who sent the message. Each one solves a critical part of the security puzzle.
Everything we do online, from our banking to our social media to our private conversations, it all rests on the strength of this mathematics. It's this constant, ongoing battle between the code makers and the code breakers. And that kind of leaves us with one final thought to chew on. As new technologies like quantum computing start to appear on the horizon, how will these fundamental building blocks need to change and evolve to protect us from the next generation of threats?